On April 20th, 2025, a NASA spacecraft named Lucy, already 4 years into an epic 12-year, 4 billion-mile journey across the solar system, swept past a small, obscure asteroid in the main belt between Mars and Jupiter, coming within just 600 miles of its surface. This asteroid, officially designated 52246 Donald Johanson, wasn't even supposed to be the star of the show. It was meant to be little more than a practice run, a warm-up exercise before Lucy's true mission targets, a swarm of ancient, unexplored asteroids trapped near Jupiter known as the Trojans. But almost as soon as the images and data started streaming back to Earth, scientists realized this so-called warm-up asteroid was hiding something genuinely strange, a peculiar, wobbling, peanut-shaped body with a surface record stretching back millions of years, telling a story of violent collision, ancient water, and slow, ongoing transformation that nobody fully expected to find. In this video, we're going to take a deep dive into NASA's Lucy mission, what makes it such an extraordinary undertaking, and exactly what scientists discovered at Donald Johanson that left even veteran researchers surprised. To understand why this discovery matters, it helps to first understand what the Lucy mission actually is, and why NASA sent a spacecraft on such an extraordinarily long, complicated journey in the first place. Lucy launched in October 2021, during a period when the world was still largely consumed by the COVID-19 pandemic, meaning the mission's launch received relatively little public fanfare compared to other high-profile NASA projects. But in the years since, Lucy has been quietly, steadily making its way across the solar system on what is genuinely one of the most ambitious asteroid exploration missions ever attempted. Its ultimate destination is a population of asteroids called the Jupiter Trojans, two enormous swarms of ancient rocky bodies that share Jupiter's orbit around the Sun, with one swarm trailing behind the giant planet and the other leading in front of it, both held in place for billions of years by the delicate gravitational balance between Jupiter and the Sun. Scientists believe these Trojan asteroids are essentially frozen relics, fossils left over from the very earliest days of our solar system's formation, material that has remained largely undisturbed for roughly 4.5 billion years. No spacecraft has ever visited them before, which means Lucy is on track to become the first mission in history to study these ancient objects up close, potentially offering scientists an unprecedented window into the conditions present during the solar system's chaotic, violent infancy. Reaching the Trojan asteroids, however, requires an extraordinarily long and complicated journey, and Lucy's mission planners have used this lengthy transit time wisely, designing the spacecraft's route to pass by several other, more conventional main-belt asteroids along the way. These flybys serve two purposes at once. First, they allow the Lucy team to test and calibrate the spacecraft's tracking systems, imaging sequences, and scientific instruments under real flyby conditions, essentially conducting dress rehearsals before the much more scientifically critical Trojan encounters begin in 2027. Second, and just as importantly, these seemingly minor detours have already produced genuinely valuable science in their own right, revealing that even the smaller, less scientifically prioritized asteroids scattered throughout the main belt can hold surprisingly complex, informative histories of their own. Lucy's very first asteroid encounter came in November 2023, when the spacecraft flew past a small asteroid named Dinky Nesh, itself named after the Ethiopian name for the famous Lucy hominin fossil that inspired the entire mission's name. Even this earlier flyby delivered an unexpected surprise. As Lucy's cameras captured detailed images of Dinky Nesh, scientists discovered that the asteroid wasn't alone at all. Orbiting closely around it was a small companion object, later named Salem, and remarkably, Salem itself turned out to be what's known as a contact binary, meaning it's actually composed of two separate lobes that have gently collided and stuck together over time. Essentially, a tiny asteroid made of two smaller asteroids fused into one. This discovery of a novel contact binary satellite orbiting Dinkinesh was itself considered a genuine surprise, hinting early on that Lucy's supposedly minor warm-up targets might turn out to be far more scientifically interesting than anyone initially expected. That pattern would repeat itself even more dramatically at Lucy's next major encounter roughly a year and a half later. Which brings us to Donald Johanson, the asteroid at the heart of this video, and the target Lucy flew past on April 20th, 2025. This asteroid takes its name from paleoanthropologist Donald Johanson, the scientist who, on November 24, 1974, made one of the most famous discoveries in the history of human origins research, unearthing the fossilized skeleton of an early human ancestor in Ethiopia's Great Rift Valley, a set of remains that would come to be known worldwide simply as Lucy, and which directly inspired the name of NASA's spacecraft decades later. In a fitting piece of scientific symmetry, Lucy's flyby of the asteroid named after Johanson occurred almost exactly 50 years after his original history-changing fossil discovery back on Earth. As Lucy approached Donald Johanson, scientists already had some preliminary information about the asteroid gathered from Earth-based telescope observations, which had hinted that it was elongated in shape and rotated relatively slowly. But nothing fully prepared the mission team for what Lucy's cameras actually revealed once the spacecraft made its close approach, coming within roughly 600 miles of the asteroid's surface. Rather than a simple, elongated rock, Donald Johanson turned out to look strikingly like a peanut, an asteroid composed of two distinct lobes, one noticeably larger than the other, connected together by a narrower, pinched neck in the middle. According to Dr. Hal Levison, the principal investigator for the entire Lucy mission at the Southwest Research Institute, Donald Johanson possesses what he described as strikingly complicated geology, a description that would prove to be something of an understatement once the full scope of the asteroid's strange features became clear. One of the most immediately noticeable and genuinely unexpected findings involved the asteroid's rotation. Scientists generally expect small asteroids like Donald Johanson to spin in a relatively tidy, predictable way, rotating steadily around a single, stable axis, much like a top spinning smoothly on a table. But Donald Johanson doesn't behave this way at all. Instead, detailed tracking of the asteroid's motion revealed that it tumbles through space in an irregular, complicated fashion, wobbling rather than spinning cleanly, a chaotic rotational state that scientists don't often observe so clearly in small asteroids like this one. According to Dr. Simone Marchi, deputy principal investigator of the Lucy mission and lead author of the scientific study analyzing this flyby, this wobbling, tumbling motion, turned out to be one of many surprising things the mission team learned since Lucy's encounter with the asteroid, offering an important, unexpected clue about the object's long, turbulent history. To understand why this tumbling motion mattered so much to scientists, it helps to understand a little bit about how asteroids like Donald Johanson typically form in the first place. Researchers determined that Donald Johanson isn't really a single, original object at all, but rather a fragment left over from a much larger asteroid that was violently smashed apart in a massive collision roughly 155 million years ago, deep within the main asteroid belt between Mars and Jupiter. This ancient parent body, identified by scientists as the 45-mile-wide asteroid known as 163 Erigone, was struck by another object with enough force to shatter it into numerous smaller pieces, sending fragments scattering outward, with Donald Johanson being just one of the resulting chunks. Because this particular collision and breakup event happened relatively recently in geological terms, at least by the standards of a solar system that's roughly 4.5 billion years old, Scientists studying Donald Johanson essentially have access to a rare, well-preserved, time-stamped example of exactly how small bodies evolve and change in the millions of years immediately following this kind of violent family-forming collision. The asteroid's strange, complicated wobble is likely a direct, lingering consequence of this ancient impact, a kind of frozen echo of the chaotic, disruptive event that created it in the first place, still detectable in its motion tens of millions of years later. Beyond its unusual shape and its irregular tumbling motion, Lucy's instruments uncovered something else about Donald Johanson that genuinely surprised the mission scientists. Clear evidence of ancient water. Using its onboard spectrometers, instruments designed to analyze the specific wavelengths of light reflected and absorbed by different minerals on the asteroid's surface, Lucy detected the presence of iron-rich clay minerals scattered across Donald Johanson. These particular minerals don't simply form on their own, floating freely through space. Clay minerals like these require the presence of liquid water at some point in the past, chemically altering and transforming the asteroid's original rocky material into these distinctive, water-formed compounds. This finding strongly suggests that Donald Johanson, or more precisely, the larger parent asteroid it broke away from, once contained liquid water, actively interacting with and reshaping its internal chemistry long before that catastrophic collision tore it apart 155 million years ago. Given how cold, dry, and inhospitable most asteroids in the main belt appear on their surfaces today, finding this kind of direct mineralogical evidence for ancient liquid water represents a genuinely significant discovery. Adding Donald Johanson to a growing list of small, seemingly unremarkable asteroids that turn out to have surprisingly wet, complex chemical histories buried within them. Interestingly, this evidence of ancient water fits into an even larger, more surprising piece of the puzzle regarding where Donald Johanson's parent asteroid actually originated. Follow-up analysis published in the scientific journal Science suggested that the carbon-rich, water-altered material making up Donald Johanson likely didn't form in its current location within the main asteroid belt at all. Instead, evidence points toward this material having originally formed much farther out in the solar system in a colder, more distant region where conditions would have been more conducive to preserving ice and water-related chemistry, before later being gravitationally shoved inward toward its current position between Mars and Jupiter. This kind of large-scale migration, material originating far out in the solar system's colder outer regions before eventually being redistributed inward over millions or billions of years, offers scientists valuable insight into the complex, dynamic processes that shaped our solar system's architecture long after its initial formation. Processes that continued reshuffling material across enormous distances long after the planets themselves had largely finished forming. The complexity didn't end there. Detailed imaging of Donald Johanson's surface revealed a landscape covered in features that scientists found unusually varied and informative, so much so that in October 2025, the International Astronomical Union officially approved a whole new set of names for distinct surface features identified on the asteroid, honoring significant sites and discoveries from the field of paleoanthropology, fitting neatly with the asteroid's own namesake. According to Dr. Marchi, mapping and naming these landscape features felt genuinely exciting, comparing the process to the way human explorers throughout history have mapped and named notable features whenever they've encountered a new, previously unexplored landscape here on Earth. The asteroid's smaller lobe showed relatively fewer craters compared to its larger lobe, which displayed a noticeably higher concentration of impact scars, hinting at a complicated, uneven history of bombardment and surface evolution across the two connected sections of this peanut-shaped body. Scientists also used detailed gravitational mapping techniques, creating false color overlays of the asteroid's surface slopes to better understand how loose surface material might behave and potentially shift across Donald Johansson's uneven two-lobed terrain over time, adding yet another layer of geological complexity to what was originally expected to be a fairly straightforward, unremarkable practice-run target. Perhaps what makes all of these findings so genuinely surprising is the simple fact that Donald Johansson was never meant to be a major scientific priority for the Lucy mission in the first place. As NASA's own mission scientists have repeatedly emphasized, both Dinky Nesh and Donald Johansson were considered secondary, almost incidental targets, useful primarily as engineering tests and instrument calibration opportunities ahead of Lucy's much more scientifically important encounters with the Trojan asteroids still to come. And yet, both of these seemingly minor warm-up targets ended up delivering genuinely unexpected, scientifically valuable discoveries. Dinky Nesh's surprising contact binary companion Selam, and now Donald Johansson's strange, wobbling motion, its complicated two-lobed shape, and its clear mineralogical evidence of ancient liquid water. According to Tom Statler, the Lucy mission's program scientist at NASA headquarters, these early images and findings continue demonstrating the tremendous capability of the Lucy spacecraft as what he described as a genuine engine of discovery, opening up entirely new scientific questions, even at targets nobody expected to be particularly remarkable going in. This pattern of unexpected discoveries at supposedly minor targets carries an important broader lesson for planetary science as a whole. Even small, seemingly unremarkable asteroids, objects easily dismissed as unimportant leftover rubble scattered throughout the solar system, can preserve genuinely detailed, informative records of collision, internal chemical change, shifting surface landscapes, and even ancient water, provided scientists have the right instruments and the right opportunity to study them up close. For decades, much of what astronomers knew about small asteroids like Donald Johansson came exclusively from distant Earth-based telescope observations, methods capable of estimating rough shape, size, and rotation period, but almost entirely blind to the kind of intricate surface detail, precise rotational behavior, and detailed mineralogical composition that a close spacecraft flyby can reveal. Lucy's brief but revealing encounter with Donald Johansson serves as a powerful demonstration of just how much scientific value remains locked away within objects that, from Earth, appear as little more than faint, featureless points of reflected light. Beyond its immediate scientific findings, Donald Johansson's flyby also served its originally intended, more practical purpose extraordinarily well, testing and validating the Lucy spacecraft's technical systems ahead of its far more demanding future encounters. The successful navigation, precise imaging sequencing, and successful data collection achieved during this April 2025 flyby gave the Lucy mission team high confidence that both their spacecraft's hardware and their own ground-based operational procedures are working exactly as intended, a genuinely important confirmation before the mission moves on to its true primary objectives. Lucy's onboard instruments, including its LaLaurie long-range imaging camera, its L. Ralph color imager and infrared spectrometer, and its LTES thermal infrared spectrometer, all performed their designated roles successfully during the encounter, collecting the detailed imagery and spectral data that scientists would spend the following months carefully analyzing to piece together Donald Johansson's complicated, surprising history. It's also worth spending a moment on the sheer engineering challenge involved in pulling off a flyby like this one at all. Donald Johansson is a small object, roughly half a mile across at its narrowest, and only about twice the length of Central Park at its longest, drifting through the vastness of the main asteroid belt at tremendous speed. Successfully targeting a flyby distance of just 600 miles from an object this small, located hundreds of millions of miles from Earth, requires an extraordinary degree of precision in trajectory planning, navigation, and real-time course correction. Mission controllers had to calculate Lucy's approach with pinpoint accuracy months in advance, accounting for the asteroid's exact orbital position, its rotation, and the spacecraft's own velocity, all while managing communication delays of many minutes between Earth and the spacecraft, meaning Lucy's onboard systems had to execute much of the encounter autonomously, without the possibility of real-time human intervention if something unexpected occurred during the critical moments of closest approach. The fact that Lucy successfully captured detailed, sharp imagery of Donald Johansson's surface during this brief encounter, including the time-lapse sequence showing the asteroid's peanut shape rotating into view as the spacecraft sped past, stands as a genuine testament to the precision of both the spacecraft's engineering and the mission team's navigational planning. The timing of data return also played an important role in how this discovery unfolded for the public and scientific community alike. Because Lucy's onboard systems could only transmit a limited amount of data back to Earth at any given time, given the enormous distances involved and the physical limitations of deep space communication, the full scientific picture of Donald Johansson didn't emerge all at once. Initial images from the LaLaurie camera arrived first, giving scientists their first tantalizing glimpse of the asteroid's unusual peanut shape within days of the encounter. But data from Lucy's other instruments, the LaRalph Color Imager and Infrared Spectrometer, and the LTES Thermal Infrared Spectrometer, took considerably longer to retrieve and analyze, with the mission team continuing to process and interpret this additional information over the following weeks and months. This is actually a fairly typical pattern in deep space missions, an initial wave of exciting, visually striking images capturing public attention, followed by a much longer, more methodical process of scientific analysis, as researchers gradually work through the full data set to build a complete, evidence-based understanding of what they've actually found. The detailed conclusions about Donald Johansson's water-altered minerals, its likely place of origin farther out in the solar system, and its complicated collisional history only fully emerged following this extended period of careful scientific analysis, eventually being published together in the peer-reviewed journal Science more than a year after the actual flyby took place. It's also worth pointing out how this discovery fits into a broader pattern that planetary scientists have increasingly recognized over the past few decades. Asteroids are far less uniform and far more individually distinctive than older, simpler models once assumed. It used to be common for scientists to think of asteroids in fairly broad, generalized categories: rocky bodies, metallic bodies, or carbon-rich bodies, without expecting enormous variation or complexity within each individual object. But as spacecraft have visited more and more asteroids up close, from Lucy's own targets to missions like OSIRIS-REx at asteroid Bennu and Hayabusa-2 at asteroid Ryugu, a much more nuanced picture has steadily emerged. Individual asteroids, even relatively small ones like Donald Johansson, can have remarkably complex, individually unique histories, shaped by specific collision events, chemical alteration processes, and even long-distance migration across the solar system. Each new close-up encounter tends to reveal a level of geological and compositional complexity that surprises the scientists studying it, reinforcing the growing understanding that truly understanding any given asteroid requires direct, close observation, rather than broad generalizations extrapolated from more easily observed but distant targets. Looking ahead, Lucy's true scientific mission is only just beginning. Having successfully completed its practice run encounters with both Dinkinesh and Donald Johansson, the spacecraft will now spend the remainder of its journey traveling deeper through the solar system, on course to reach its first genuine primary target, a Jupiter Trojan asteroid named Eurybates, in August 2027. From there, Lucy is scheduled to continue on an extraordinarily ambitious tour, ultimately visiting a total of 11 different asteroids over the full course of its 12-year mission, including several more Trojan asteroids clustered within Jupiter's leading and trailing swarms. These Trojan asteroids are believed to represent genuinely primordial material, fossilized remnants, preserved largely unchanged since the earliest, most chaotic period of our solar system's formation, offering scientists an unprecedented opportunity to study conditions and processes that occurred over 4 billion years ago, long before Earth itself had even fully formed. If Lucy's brief secondary encounters with relatively minor, seemingly unremarkable, main belt asteroids like Dinkinesh and Donald Johanson could already produce such surprising, scientifically rich discoveries, anticipation is running high throughout the planetary science community regarding what genuinely ancient, previously unexplored primary Trojan targets might reveal once Lucy finally reaches them. It's also worth taking a moment to appreciate the broader significance of what missions like Lucy represent for our understanding of the solar system as a whole. Every asteroid, every small, seemingly insignificant rocky body scattered throughout the vast space between the planets, carries within it a physical record of the specific conditions, collisions, and chemical processes it experienced since the solar system's earliest days. Larger planets like Earth have been so thoroughly reshaped by billions of years of volcanic activity, plate tectonics, erosion, and other transformative geological processes that most direct evidence of their earliest formation has long since been erased or buried beyond easy detection. Asteroids, by contrast, particularly smaller ones that have never been large enough to sustain this kind of intense internal geological activity, often preserve their original material and structure in a far more pristine, unaltered state, effectively functioning as natural time capsules. By studying objects like Donald Johanson in close, careful detail, scientists aren't simply satisfying curiosity about one strange, peanut-shaped rock. They're gradually piecing together a far more complete, detailed picture of the violent, chaotic, and chemically complex processes that shaped our entire solar system during its earliest, most formative years. It's also worth considering what all of this means for the still unresolved question of how water and organic material spread throughout the early solar system, a topic directly relevant to understanding how life eventually emerged here on Earth. Scientists have long debated exactly how our own planet, which likely formed too hot and too close to the sun to retain much of its original water, eventually ended up with oceans covering most of its surface. One leading theory holds that much of Earth's water arrived later, delivered by collisions with water-rich asteroids and comets that formed farther out in the solar system before being gravitationally redirected inward, colliding with the young Earth over hundreds of millions of years. Discoveries like the one at Donald Johanson, water-altered minerals found within an asteroid that likely originated farther out in the solar system before migrating inward to its current position in the main belt, provide exactly the kind of direct physical evidence scientists need to test and refine this theory. Every asteroid found to carry these kinds of water-related chemical signatures adds another small piece of supporting evidence to the broader picture of how water-rich material may have been distributed and redistributed throughout the early solar system, potentially including the very same kind of material that eventually helped fill Earth's oceans billions of years ago. This kind of collaborative, incremental scientific effort also highlights how much modern planetary science depends on teams of researchers working together across different institutions. The study detailing Donald Johanson's water-altered minerals and its likely origin farther out in the solar system involved contributions from multiple research groups combining expertise in spacecraft imaging, spectroscopy, orbital dynamics, and asteroid family classification, all working together to piece together a coherent picture of one small asteroid's surprisingly complicated 4-billion-year history. This kind of interdisciplinary collaboration has become increasingly standard in planetary science, reflecting just how many different specialized skills are required to fully interpret the data returned by a single brief spacecraft flyby, and how much richer the resulting scientific picture becomes when researchers from different specialties combine their perspectives on the same shared dataset. As we bring this video to a close, it's worth reflecting on just how much genuine scientific value can emerge from even the smallest, most overlooked corners of space exploration. Donald Johanson was never supposed to be Lucy's main event. It was simply a warm-up, a chance to test cameras and tracking systems ahead of the spacecraft's far more anticipated journey to the ancient Trojan asteroid surrounding Jupiter. And yet, this seemingly minor detour delivered a genuinely strange, unexpected story, a wobbling, tumbling, peanut-shaped fragment of a much larger asteroid violently shattered apart 155 million years ago, bearing clear mineralogical fingerprints of ancient liquid water, and preserving a complicated, cratered landscape detailed enough to earn its very own set of officially recognized surface feature names. If a supposedly unremarkable practice target could surprise scientists this much, it's hard not to feel genuine excitement about what Lucy might uncover once it finally reaches the truly ancient, never-before-explored Trojan asteroids still waiting for it, patiently orbiting alongside Jupiter, roughly 2 years from now. If you enjoyed learning about this incredible discovery, make sure to like this video, subscribe to the channel for more deep dives into space exploration and astronomy, and let us know in the comments what surprised you most. The asteroid's strange peanut shape, its unexpected wobble, or the ancient evidence of water hidden within its rocky surface. We'll see you in the next video with another incredible story from the far reaches of our solar system.